Hi, my name is Giles Heron, and today I want to give you a brief introduction to an open source project called Media Streaming Mesh. So before I describe Media Streaming Mesh, I thought it was worth explaining why we might need it. And to do that, I've divided the world of applications using this 2x2 matrix as beloved of management consultants. So in one axis, we have whether an application is real-time or non-real-time. In the other axis, we have whether it is interactive, that is having request-response semantics, or streaming, that is having pub-sub semantics. So my contention would be that Kubernetes is squarely focused on web applications, or at least was initially, and that those are in this top left corner, so non-real-time and interactive. So you make a web request, and then you get a response from the server. Now, in Media Streaming Mesh, we're focusing on live media, and so that's the opposite corner of the matrix. So typically, real-time media apps use a protocol called RTP, the real-time protocol, and it's very much streaming, so pub-sub. Now, I've said that this taxonomy is fuzzy, and fuzzy really because the lines aren't always clear, however clear they might be in the slide. So take the example of a video conference. We perceive a video conference as interactive because we're interacting with the other people, but when you look at the mechanics underneath that, what you'll find is, in fact, each of us will be publishing our audio and video, and the other people on the conference will be subscribing to those streams. So it's very much pub-sub under the covers. And in fact, very often you'll see the real-time protocol being used, RTP, as the fabric for video conferences. And likewise, how real-time is real-time? I'm old enough to remember analog television. And in the old days, you would watch television, the news would be coming up perhaps at 6 o'clock. And at least here in the UK, you'd see a clock on the screen counting up the seconds as it went towards the hour. Now we've lost that in the world of digital television. And the reason we've lost that is because compression and decompression take time. And so now the time when the video is being filmed on the camera or put onto the system is not the same as the time when I receive it. Now, of course, that's even more extreme for over-the-top streaming. So if I'm watching a football match on cable or on satellite, I might be lagging by a second or two, but my friend who's watching over the top through the internet might well be 30 seconds or even a minute behind me. So I have to be very careful not to text saying, wasn't that a great goal? Because they may well not have seen that goal yet. So let's quickly look at how video gets from a camera all the way to a viewer. So back to our football example, there might be multiple cameras in the stadium. Maybe there's an outside broadcast facility, or maybe all the camera feeds are coming back to the studio. But either way, there's a mixing step where you have to select which camera feed you're going to take. You perhaps add on a strip at the top saying what the score is. Maybe there are alerts at the bottom. So that whole stage in broadcast is typically called the contribution network. Having got that 4K HDR uncompressed stream, for example, it then needs to be distributed towards the viewers. And so now we come to encoding. Typically today that would be close to the studio, but over time I could see that moving into the cloud because really it's just compute. So encoding is different resolutions, different bit rates, adding content protection, etc. And then we have what's called the distribution network, feeding that video out towards the subscriber. So it could be towards terrestrial antennas, cable or IPTV head ends, satellite networks, content distribution networks, etc. And then you have that final delivery to end users, which in this case I've shown CDN caches that could be at the edge or inside an ISP network using HTTP live streaming, for example, to deliver that content to the end user. Now with Media Streaming Mesh, we're aiming to cover all of this ultimately, but really our initial focus would be on encoding and on the distribution network. The contribution network, that's dealing with very high bit rates, very low tolerance for packet loss, for jitter, and also, of course, very often genuine hardware devices. This isn't just compute. You have physical cameras and mixers and things. So over time, I think we'll see ourselves in that segment, but initially more in distribution. In terms of the final delivery to subscribers, I think we've prototyped that using, for example, real-time protocol over QUIC. Longer term, there will be efforts there, I think, but for now, I think we'd assume that we'd get as far as filling a cache, but the final delivery would be over HTTP. Now, of course, there are many other use cases for Media Streaming Mesh outside of live video. So, for example, you could have IoT cameras, or you could have web conferencing, for example. And so, yes, ultimately, there are many use cases for this technology. I'm just showing one of the use cases here. So, how does internet streaming work today? This is HTTP live streaming, and this is how I would be watching a football match today if I was watching over the top. And so my client, which could be my TV or my web browser, would connect to a web server and it would retrieve a media playlist. Now, if I was watching a movie, then that media playlist could have a large number of segments, each describing a chunk of the video, 1 or 2 seconds worth perhaps. But in the case of a live event, you don't want to be so far behind, so you're only going to see a few segments. And so those segments are returned to the client, and the client can then get each segment from that playlist and then play it out. And so there's always a trade-off here in terms of reliability versus latency. So the more segments you're willing to buffer up, the easier it is to adjust to packet loss and congestion, but then you're further behind. And what you sometimes see is you'll get the video will freeze and then you'll see it zooming faster than real time to catch up again. And there is work today on things like low latency HLS, but still today, for the football, for example, I typically see 30 or 40 seconds of lag. And that could be because we're going through multiple stages of content distribution. And I think it's hard to see us ever getting to sub-second type delays in this model. And of course, each time you play out the last segment, you repeat and grab another media playlist. So how does live video over IP work today? Well, there are probably a couple of different models. Both of them depend on the real-time protocol or RTP. So just as HTTP is a key protocol for web apps, RTP is the key protocol for live media, and that's what we're optimizing in media streaming mesh. So the first approach is where a client and a server are both using a TCP channel, and they use that to negotiate the UDP ports they will use for that RTP media. So for example, I could connect to my security camera at home from my computer, it would use RTSP, and then my computer would get the media streams from the camera. So the URL that I ask for, the camera will return some media streams and say, okay, I've got a video stream, for example, and I've got an audio stream. So the client will then negotiate UDP ports with the server for each of those streams, and then it will start playing them. And at that point, the server will send the media to the client over UDP. But the important point here is the UDP ports we use are ephemeral. They're not negotiated ahead of time. They're negotiated at runtime. So a second approach to video over IP is multicast. So in this case, you might have a camera that's always sending, and this can be used in multiple different environments. We see it a lot in contribution video. You also see it in IPTV, so where a service provider is providing a managed IPTV service. So in this case, the stream is always there. So how do you find the stream? That's the question. There could be a REST API. It could be that your set-top box in IPTV is pre-programmed with the mappings from channels to multicast groups. Or, as in contribution video, you might have a controller that connects to the sender, gets the media information, then sends that media information to the receiver. The receiver can join that multicast group, and finally traffic can flow. So, when we look at how we might do real-time media in Kubernetes, we might look at some of the existing mechanisms. So, first off, let's look at kubeproxy and node port. Well, they're fine for TCP applications, including HTTP and for UDP. In fact, if you want to expose those outside the cluster on the ports you want them on rather than high ports, you can't use node port, you have to use an ingress or a load balancer. But what you can't do is support these real-time media apps. And there's problems there that really come down to those two previous slides. So firstly, kubeproxy is network address translation, and so it won't see that port negotiation that happens on your TCP control channel for RTSP, for example. Equally, however, most Kubernetes CNIs don't support IP multicast, and so you can't support that second model. Or you might look at service meshes and load balancers. These are great for TCP. They're fantastic for HTTP apps because you can do things like URL routing, load balancing, circuit breaking, etc. Today, they typically don't support UDP, and I think when they do, it's more likely to be driven by the requirement for HTTP v3 and for QUIC, and that runs on top of UDP. But they don't support real-time media. So another approach would just be to use host networking. So run your media pod in the host namespace. So that's great. What's not to like? Well, one thing, and that one thing is you can only have one pod per node because only one entity can own any specific port on the node. There's also a bit of a security issue here because you're now trusting that pod as to what it does, what ports it opens, etc. So this could be fine, perhaps, if you're running on virtual machines, but clearly in a bare metal environment, you're going to underuse your host. So that's where media streaming mesh comes in. The goal is to handle real-time media. We're going to proxy the control plane. That control plane proxy will see the UDP port negotiation that happens there. We'll also proxy the RTP data plane, so we can convert from unicast to multicast. We can create an application layer tree, effectively fanning the data out to all the entities that need it. We can also support TCP and UDP, since RTP typically runs over UDP but can also run over TCP, and we'll be proxying at that layer as well. While we won't support HTTP v3, we will support QUIC, so we can map RTP directly onto QUIC. So I've coloured that one in orange. I think you can just see from this diagram that perhaps it makes sense to use service meshes for the left-hand side of the diagram and media streaming mesh for the right-hand side. I think it's also worth saying, with reference to QUIC, that longer term I can see QUIC really filling in all 4 cells in that 2x2 matrix I showed earlier, so covering all different types of application. So here we have the demo set up, and there are 3 main entities I want to describe here in Media Streaming Mesh. We have the control plane I've already mentioned, so we run one of those per cluster. That runs as a Kubernetes service. It's written in Golang, and the goal there is to make the control plane pluggable, so that if you want to replace our RTSP implementation with, for example, RIST or SIP, then you can do that. Then we have the RTP proxy, which we show in red, so that's our data plane. Currently that's also written in Golang. That's very much a prototype. I plan to rewrite that using asynchronous Rust to get performance. We'll also look to implement DPDK, so Intel's Data Plane Developer Kit, to talk to the NIC, and eBPF to talk to the pods, so we'll get high performance that way. And then we have the stub. Now the stub has a couple of different functions. So we've written that in Rust. One function that you can see here is, as the client connects, the stub intercepts the control plane traffic. So effectively here it's acting as an ingress, and then terminates that TCP connection, and then sends that control plane traffic to our control plane using gRPC. So now the control plane will use, for example, the Kubernetes API and or DNS. So it will find, for example, that the URL it's being asked for has a path at the end of it. It will match that against a Kubernetes service. It will find an endpoint for that service, and it will talk to that endpoint. And the stub running alongside that endpoint, so we'll have an auto-injected stub there. That stub will also then send TCP control plane traffic to, in this case, an RTSP server that's running in a pod, really emulating a camera feed. And here we see the next function of the stub, which is, it is possible with RTSP to interleave the RTP data over the TCP connection that's used for the control plane. And this is what this fake camera feed is doing in this case. And here we can see how the stub is going to be able to break out that traffic and send it as UDP direct to the RTP proxy, which you just saw pulse, and that was the control plane programming the RTP proxies, so that now this RTP proxy knows to send traffic to the remote RTP proxy where the user was connected, and that will then send the RTP traffic back to the user. Now the key with the data plane as we move it to Rust is that, just like the control plane, we want to make it pluggable, and ideally we want to use WebAssembly for that. So you can plug in additional filters that do things like forward error correction or NAC-based error correction or congestion control, and that makes those easy to contribute. So now, if a second client arrives and connects at the same node, what we'll see is the control plane gets the control plane traffic again, but it knows that it already has a stream running in this instance. And so it simply tells the RTP proxy where that client's connected to send to the new client as well. So let's look at the benefits we're aiming to get from Media Streaming Mesh over and above running multiple real-time media apps on each node. So the first thing to say is, looking at the top half of this picture, we're looking to get the same kind of benefits for real-time apps that Service Mesh delivers for web apps. So fundamentally, observability and security. So we want to track the state of each stream in the network and see where the sender is and where the receivers are. But more importantly than that even, we want to be able to measure the jitter and packet loss. We can do that because the RTP header has sequence numbers and timestamps. In terms of security, we want to authenticate using SPIFFE, authorize using OPA, and encrypt the traffic as it flows from node to node. And then looking at the bottom half, these are specific things we want for real-time media. So in terms of distribution, I mean having those optimal replication trees, but also being able to minimize latency and jitter as well as just measure it. And in terms of deployability, this is where having one control plane per cluster, a data plane per node, the possibility of remote nodes that are just edge nodes with no control plane that use a cloud-based control plane, that's how we optimize the footprint, which is particularly important in edge deployments. So really what I want to finish with is just to say that we'd like you to participate. So Media Streaming Mesh is very much a work in progress, but it's all in open source, and we have the GitHub URL here. And please do collaborate with us, whether with contributing code or use cases. The QR code here will take you to the website. That also has a link to the GitHub and to our Slack channel. And there on the bottom right, you can see different ways to reach me. So please do get in touch. And here's hoping that in future, when goals get scored in football matches, we see them in real time. Thank you.